Hassler here. All right, I'm going to work through the 1.11 notes with you on defining continuity for a function at a specific point. And the first thing I would like you to do is take a look at 1 and the graph that goes with 1. It says use the graph of f to complete each part. So in problem 1, your job is to name the types of discontinuity at the given x value. I encourage you to press pause and try this on your own, and then hit play and see if your answers line up with mine. Okay, so when I'm looking at x equals -1, x equals -1 is right here. And it looks to me like we have a vertical asymptote. And so that would be infinite discontinuity occurring at x equals -1. You don't have to write the word discontinuity every time. I just wrote it this time, and I'm not going to write it next time. So at x equals 2, and I've got x equals 2 right here. At x equals 2, on my curve, I have this hole. Now, I do have a point defined somewhere else, and that just means that point was removed from my curve and placed somewhere else. When I have a hole, I technically have what we call removable discontinuity. You got to stop and think about how to spell that, which is the same thing as saying a hole, but you won't see the word hole in multiple choice options through AP. And so it is my job to remind you that removable is the correct terminology for that particular type of discontinuity. Okay, the next one that is asked about is x equals 7. And so here's x equals 7. And not only do I have a hole in the one location, but my curve kind of breaks apart and starts at a different y location before moving on. This is where we get that piecewise function happening. And because of this, my function is jumping from this y value all the way to this y value. Remember, we call this a jump discontinuity. Okay, how about at x equals 4? It's so hard to pick which color, right? We'll go with orange. At x equals 4. All right, so here's x equals 4. And as I look up at my curve, well, there's no infinite discontinuity. There's no hole there, so no removable discontinuity. And there's no breakaway in my graphs, no jump discontinuity. In fact, because none of those discontinuities occur, we say that there's no discontinuity. And there's no discontinuity because f of x is actually continuous at x equals 4. And I'm going to write that complete statement because that complete statement is true. And there is a definition for continuity. There are conditions that must be met in order for continuity to exist. And it can't just be that continuity is the fact that, I'm going to grab red here, the fact that you can start at one part of your graph and move through the entire portion of your graph without picking up your pen or pencil or marker. Yeah, that would be a way to state continuity, is that I don't have to pick up my marker, versus here at x equals 2, I'd have to pick up my marker, jump over that hole or move past the hole before I can keep going. There is a mathematical way to describe continuity, and that's what we're going to do down here. So the formal definition of continuity at a point is that a function is continuous at x equals c only if the following 3 conditions are met. So the first condition is that f of c is defined. And what that means is that the actual point, the ordered pair c comma f of c, is graphed for the curve. In other words, if I put the x value into the function, I get an actual numerical value out. There is a point that can be plotted. Okay, so that point has to be defined. The next condition is that the limit as x approaches c for my function has to exist. And remember that in order for a limit to exist, the limit as x approaches c from the left side of my function has to equal the limit as x approaches c for the right side of my function. I'm going to come back up here to my picture and delete some of this here. Okay. When I take a look at what this says, f of c is defined. Okay, well, I'm going to look at x equals 2 again. F of 2 is defined, right? I have this defined point in black. And the limit as x approaches c of f of x exists, right? When I look at what's coming in on the left side, I'm approaching a y value of 2. As I come in from the right side, I'm approaching that same y value of 2. So I'm defined and my limit exists. However, I'm still not continuous there. I still have a hole there on the actual curve. Versus when I look at x equals 4, I do have a point plotted there. And it's just not like a boldened point, but there's no hole there, so there's technically a point there. And the y value I approach on the left is the same as the y value I approach on the right. And so we would say this is continuous, and this is continuous because of the third condition. That where my point is defined, or where my function is defined, is the same as the output for the overall limit. Okay? And so our third condition is that f of c, my defined point, is equal to that overall limit as x approaches c of f of x. Okay? And I'm just going to say that in words. Defined point equals or matches. Defined point matches the overall limit. Okay? Now, it's going to be our job to verify that algebraically. I can verify that graphically. Graphically, I can pick out the discontinuities. Graphically, I can see that I have a smooth curve. But algebraically, I can't always look at a graph to make that determination. Okay? So this is what I'm going to do. I'm going to show you how to do this using 2 examples. And your job is to complete a Delta Math assignment related to graph discontinuities and determining whether a function is continuous or not, graphically or algebraically. So state whether the function is continuous at the indicated x value. Justify your answers. And justify your answers means that you want to show that the 3 conditions are met or not met. I'm going to say met or not met. Okay? So you have to work through those 3 conditions. All right, so for at x equals -1, at x equals -1, I first have to determine, I'll do this, sorry. I first have to determine if f of -1 exists. And in order to do that, I'm just going to evaluate f of -1. So I need to look and see, okay, where would that be? Well, that would be, hello. It doesn't want to let me do it. There we go. Box highlight. That's what I want. There we go. Sorry about that, friends. That's going to be this one right here because that's where the equal bar for x is with the -1. Okay, so I'm going to evaluate f of -1, which is equal to -1 plus 2, which is 1. So f of -1 equals 1. The next condition means that I have to check if the limit as x approaches -1 for my function exists. And in order to do that, I need to check if the limit as x approaches -1 from the left of my function is the same as the limit as x approaches -1 from the right of my function. To be very clear, you need this notation. If you are not showing this notation, then you are not justifying your answers and you do not have evidence to state yes or no whether the function is continuous. So everything that I write is what you need to write. Okay, so the limit as x approaches -1 from the left, well, that's going to be actually this function right here. Okay, and so when I go to evaluate that, I've got -1 squared minus 2 times -1 plus 1. So what is that? 1 plus 2, which is 3, plus 1 is 4. And as I approach -1 from the right, that's my yellow highlighted function, which we technically already evaluated to be 1. And what I notice is that these two outputs are different. So what I'm going to say is this. I'm going to say therefore. And in math, the symbols for therefore are these 3 dots that make up a triangle. Therefore, because mathematicians are lazy and we don't want to write everything out, therefore the limit as x approaches -1 overall for my function does not exist. And if that overall limit does not exist, then f of x is not continuous. Right? All 3 conditions must be met. Condition number 2 was not met. And I'm going to say it's not continuous at, I'm going to specify, we need to be specific, at x equals -1. Okay? I don't need to further look at the third condition because the second condition wasn't met. Once one of the conditions is not met, there's no need to move on to any of the other conditions. Okay, so let's take a look at whether or not my function is continuous. That's what I'm trying to answer, is my function continuous at this time at x equals 2. All right, again, the first thing I have to check is whether or not f of 2 exists. And f of 2 is actually going to come from this bottom function here. That's where the equal bar is. And so f of 2 is 2 squared, which is 4. Okay, that exists. The next thing I need to check is whether or not the limit as x approaches 2 for my function exists. And in order to make that determination, I need to look at the limit as x approaches 2 from the left of my function. Well, that's going to be the x plus 2 function, and 2 plus 2 is 4. And I need to check the limit as x approaches 2 from the right side of my function. And that's the 2 to the x function. So 2 to the second is 4. And hey, this time those things match. Okay? And the last thing that I need to verify is, does f of 2 equal the limit as x approaches 2 for my function? Yeah. We showed that 4 is the same as this overall limit, which is 4. And so, yes. And so in this particular case, my final statement would be, therefore, f of x is continuous at x equals 2. So it was not continuous at x equals -1. That means I would have some sort of jump discontinuity, right? 2 different y values as I move in towards the x value of -1. But I am continuous when x is equal to 2. All right, so you're going to use this information to help you complete your Delta Math assignment. And if you have any questions, feel free to ask me in class.